We're starting a new section on crystallography, and crystallography is basically the study of crystals. And so we're going to talk about how to describe crystals in various ways throughout this section. All right, so for this module, I want to start our discussion of crystallography by looking at crystal systems and, after that, Bravais lattices. So, up to this point, we've talked about cubic and we've talked about hexagonal as various geometries that we can look at in terms of crystals. But as you might have guessed, there's going to be more than just those two types of crystal systems. So let's kind of look at some of the basics here. So we have a unit cell. We've been kind of talking about that in our system so far, but it's basically the smallest repetitive volume that contains the entire or the complete lattice pattern of the crystal. So it's the smallest thing that we can repeat over and over again, right? And so here is a very generic unit cell, the most generic, where we have three lattice parameters: A, which we're used to, which defines the length of the volume along the x-axis, B along the y-axis, and C is the height or the length along the z-axis. And then there's angles, where gamma is the angle between the x and y, alpha is between the axes x and z, and beta is the angle between x and z. So those define the crystal the unit cell. So A, B, and C are the lattice constants, and we have angles alpha, beta, and gamma. And so what we're going to talk about is we're going to talk about 7 different systems and then 14 crystal lattices, and we'll get to both of these in the next slides. So let's look at the crystal systems first. So when we talk about crystal system, we're basically defining the unit cell geometry, right? The shape of the unit cell. So it's only talking about that volume. So the cubic crystal system was a cube, right? And so we have A, B, and C are all equal, so we just call them A, and then the angles are all 90. So we've defined those lattice parameters, and so it's just a cube. So the cubic system, though, we saw different cubic versions, right? We saw simple, we saw BCC, we saw FCC, and we also saw diamond cubic, right? So even though it's cubic, that just defines the system. If we want to talk about a lattice, we take that geometry and then add an atomic arrangement to it. So FCC, or face-centered cubic, has atomic arrangement at each corner along with each face, right? That gives us FCC. So that's what a system and that's what a lattice are. So let's go back and let's just kind of go over all the different unique crystal systems. So we know cubic. Again, the relationships, the axial relationships, A, B, C are equal, so we just talk about A, and then the angles are all 90. And so we don't even really think about the angles, but they're all 90, right? Because we have a cube. Hexagonal, A and B are equal, but the c-axis is now different. So we talk about A and C as our two lattice parameters. And then if we go into the angles here, alpha and beta are 90, but we have 120 for gamma. Next one is tetragonal. In this case, you can think of tetragonal as like cubic, but with either a elongated or shortened c-axis, because c-axis is longer now. Everything else is the same. The angles are all 90, but one of the lengths is different. So this is kind of a rectangular prism as opposed to the cube up here. We also have rhombohedral / trigonal. And this is where all of the lengths are the same. So A, B, and C, so we only have A. But one of the angles is not 90. So or sorry, all of the angles are equal, but they're not equal to 90. I apologize for that. And then we have orthorhombic, where all the lengths are different, but they're all 90. All the angles are 90. Then we have monoclinic, where all of the lengths are different. And then we have two angles equal to 90, and then one of them is not. And then the last one here, triclinic. And this is basically that generic case where none of the lengths are the same, none of the angles are 90 or equal to each other. So this is kind of the most generic structure. And as we kind of go through these, you should kind of be aware that the ones at the top here, cubic and hexagonal, are the most what we call symmetric. So they're the most similar, right? X, Y, and Z directions are all the same, angles are all the same. And then we start to lose symmetry and things like that, where we get down to here, and basically there's no sort of the least amount of symmetry is with triclinic. And so cubic is very easy to deal with for the most part, but triclinic is very challenging when you don't have any of the lengths or angles equal. So those were systems. So now let's talk about the crystal lattices. So again, this is putting on an arrangement to the geometry. And what we find is that there is only 14 crystal lattices. So once we put arrangements onto the structure, onto the systems, there's only 14 unique crystal lattices. And because this is kind of a unique number that was basically proven by this scientist here, Bravais, they're given the name Bravais lattices, because he was the one to prove, the last person to prove that there was only 14. And so they're basically kind of all 14 are right here in this screen, but we're going to go through them more individually here. So I don't expect you to kind of memorize all of these, but I do kind of just expect you to have a general kind of knowledge of these lattices. So these are going to be the ones that you have the most the most knowledge of, because we've already talked about all three of them. And these are the cubic lattices, and there's only 3 unique cubic lattices. We have the primitive, which is sometimes we've called the simple cubic. We have the face-centered, which is indicated by F here, primitive by P, and then we have body-centered, which is by I. And if you're wondering where those numbers come from, or where those letters come from, P and F are probably self-explanatory, but the I, it's because actually all of these are from German, and so body-centered kind of translates, and I got to the translation. I don't know how to pronounce that because I don't speak German, but basically that's talking about the body-centered position in German, so it's I. So that's where those letters come from, if you are curious. So we've already talked about all these different systems. We have a basic kind of understanding of how these are arranged, but let's go on to the others. So hexagonal, we've also already talked about it as well. There's only one. There's primitive, and that's where the Highlander joke comes in, is that there's only one hexagonal crystal lattice, and it is the hexagonal close packed that we talk about. And so the arrangement, can be seen here or here. One thing to keep in mind is that when you see it drawn, you might only see the darkened part here or here. That describes the whole unit cell. We don't actually need to show the whole hexagon like you see in most images. So a lot of times you might just see this. So just the 1/3 of it. But this is also the primitive hexagonal. But there's only this one. There's no body-centered. There's no face-centered, anything like that. For the tetragonal, again, it's like cubic, but we have one axis, in this case the z-axis, which is elongated or shortened. So it's not the same length. Here they're showing it longer. And so in this case, there is 2. We have the primitive and we have the body-centered. And if you're wondering, excuse me, as we go through this, why there's only certain ones for and not others, so why there's not face-centered or and things like that. Again, these were all proved by Bravais, such that if you try to draw, for example, a face-centered tetragonal, it actually becomes another structure. So that's kind of the important thing to note here, is that I can draw a face-centered tetragonal, but it can be broken down into one of the other lattices. Again, it might take you a while to prove that, but that's what Bravais did. So same thing if we go back to this one, if we try to draw face-centered or body-centered, we would have something else. Okay, so let's go to orthorhombic now. So this one actually has 4. And this is the one where all the links are different, but the angles are all 90. And so we have primitive, we have body-centered, and then we have 2 different versions of face centering. So here with the C, this is referred to as side-centered because only one combination of faces, for example, the ones on the perpendicular to the z-axis, so this one on the bottom and this one on the top, so that's side-centered. And then you have face-centered, where all of them are covered. Here they're not just, they're forgetting to draw the other 2, but this is face-centered, so all faces are contain an atom. All right, so orthorhombic, or rhombohedral, sorry, or trigonal. These are the ones that have the non-90 degree angles. And so again, there's less and less symmetry. And so in this case, there's only the primitive version. And then monoclinic, here we have, again, even less symmetry. So all the links are different. And then we have one non-90 angle. And so the 2 versions we can have here are primitive, so an atom on each corner, and a side-centered, so where we have one direction has atoms in the center of that face. So that's what we have with C. And then the last one, triclinic, this is the least symmetry, and none of the angles or links are equal to each other. So this is the most basic type of unit cell that we can describe. All right, so one last point about systems and structures is that we have a concept known as polymorphism. So let's consider we have something like tin, the metal tin, Tin. So tin can actually crystallize, form into a crystal, into multiple different types of crystals. So if we have elemental tin, we can either have it in the white form, which is beta tin, which is in a body-centered tetragonal arrangement like we see here. But it can also form into what's called gray or alpha tin, and this has that diamond cubic structure. And so any element that has multiple structures is known as allotropy. Again, it's just basically talking about possibility of multiple structures. But in general, for materials, for solids, if it can crystallize into multiple crystal structures, we call it polymorphism. So this is not just for elements, but for any material. And so that's an important concept, because things like tin or iron or other carbon have multiple structures that they crystallize into. And so that's what we refer to as polymorphism.